Okay, this video is all about bases other than e. We've got two learning targets we're going to focus on here. The first of which is to define exponential functions that have bases other than e. And we're going to take a look at the definition of exponential function to a base a. There are some properties, and there is a couple of pages, I should say, a couple of pages in the textbook where I've clipped some things that we're going to take a look at. So the definition of exponential function to base a. If a is a positive real number where a is not equal to 1 and x is any real number, then the exponential function to the base a is denoted by a to the x power and is defined by a to the x power equals e raised to the natural log a times x. Essentially what we're saying here is our functions now don't have a base of e, they have a base of a. And it's the same idea, but e is specifically the number that is represented by approximately 2.718. A could be any positive real number. You can see here that these functions have the same laws of exponents as any other exponential functions would. And some of the properties are a to the 0 power equals 1. A to the x times a to the y equals a to the x plus y. So when you multiply common bases, you add the exponents. A to the x divided by a to the y equals a to the x minus y. So when you divide common bases, you subtract the exponents. A to the x raised to the y power equals a to the x times y power. So when you have a power raised to a power, you multiply the exponents. The definition of the logarithmic function to base a: if a is a positive real number where a is not equal to 1 and x is any positive real number, then the logarithmic function to the base a is denoted by log base a of x and is defined as log base a of x equals 1 over the natural log of a times the natural log of x. This right here comes straight from the change of base formula. And the change of base formula, if you forgot, says that log base a of x equals the log of x divided by the log of a. So it's the log of the number divided by the log of the base. But instead of using logs, which are base 10 currently, written here and here, we can use the natural log, which is just log base e. You can use any base you want. And rewriting this, since a is just a number, we can put it out front as a coefficient, 1 over the natural log of a times the natural log of x. So this result right here was written back here, just didn't show the work to get there. So if you forgot the change of base formula, there it is. Logarithmic functions to the base a have properties similar to those of the natural logarithmic function from theorem 5.2, which we discussed earlier. So the first one says log base a of 1 equals 0. And that is a logarithmic equation. If you converted it to an exponential equation, it would make sense because it would be a to the 0 power equals 1. The second rule there, property I should say, log base a of x times y can be expanded because when you multiply common bases, you add the exponents. Since logs are exponents, that expands to log base a of x plus log base a of y. Number 3, that's sort of our kick out or flick rule, where the log base a of x to the n power can get flicked out front. It's really our power to a power rule. So that equals n times the log base a of x. And then, of course, the fourth rule, if you have log base a of a quotient, x divided by y, that can be expanded and written as subtraction, because when we divide common bases, we subtract the exponents. From the definitions of the exponential and logarithmic functions to the base a, it follows that f of x equals a to the x and g of x equals log base a of x are inverse functions of each other. And of course, inverse functions have special properties. So y equals a to the x if and only if x equals log base a of y. That's just the conversion from exponential to logarithmic form. Second one, a raised to the log base a of x equals x. That's an exponential equation. If we converted it to logarithmic equation, you would see that it's true. And the third one, log base a of a to the x power equals x. Similarly, if we took that logarithmic equation and converted it to exponential, you would see that it is also true. So, the logarithmic function to the base 10 is called the common logarithmic function. So for common logarithms, y equals 10 to the x if and only if x equals log base 10 of y. And essentially what you need to know from that is if you see a log and there's no base that is defined, it is specifically log base 10, which is the most common base that we use. Here are a couple of equations where you're asked to solve for x. The first one, 3 to the x power equals 1 over 81, is an exponential equation. If you have an exponential equation and you're solving for the exponent, as we are in the first example, you can take that equation and you can write it in logarithmic form. So this would convert to log base 3 of 1 over 81 equals x. Now you'll notice this is a no calculator question. You may be asking yourself, how can I do that without a calculator? Hopefully you recognize 81. 81 is 3 to the 4th power, which means 1 over 81 is 3 to the negative 4th power. Therefore, our logarithmic equation is log base 3 of 3 to the negative 4th power equals x. And we had a property that was just mentioned earlier that said if you have log base a of a to the x power, then x is what the power is. So in this case, the answer is negative 4. So x equals negative 4 is the answer to number 1. And there is another way that you could do this particular problem. You can see in the scanned-in work below here that what they did was they logged both sides of the equation using base 3, so that on the left-hand side, log base 3 of 3 to the x simplified to x, and then they rewrote log base 3 of 1 over 81 to be log base 3 of 3 to the negative 4th, where the log base 3 of 3 to the negative 4th became negative 4. I personally like the way that I did it up in blue up here. Both ways can work. The second example we have here, you're asked to solve log base 2 of x equals negative 4. So if I come up here, this is an logarithmic equation, so I can convert it to an exponential equation, where it would be written as 2 to the negative 4th power equals x, and 2 to the negative 4th power is 1 over 2 to the 4th power, and since 2 to the 4th power is 16, this is simply 1/16. Again, I think that is easier than the scanned-in work that you're about to see below. Scanned-in work, what they did was they took both sides of the equation and they did 2 raised to the respective side, used some of the simplification rules to come up with the same answer that I did above. Solving both exponential and logarithmic equations is something that is expected. It's a prerequisite, it's a pre-calculus topic, but one that we will use from time to time as we move on to our derivative and integral rules for bases other than e, which I will do in the next video.